Just the electrical skateboard. Okay. Someone is lawn mowing outside my house. It's just this drone from down the street. Yeah, it's 2 houses over. Wonderful. Wonderful. People are mowing their lawn in the rain. Why would they do that? I think they're insane. But that's their thing that they're doing right now. They can do that because they can. Nobody's doing anything they don't want to do in this world. Cool. Okay. What we're going to look at here today is some simple gravity stuff. So what we're going to look at here today is some gravity stuff from our unit on gravitation. We're going to start off with thinking about the idea of gravitational forces. Gravitational forces, they are always attractive, meaning that if we have 2 objects, such as a star and a planet, I don't know, maybe like a pale blue dot, something like Earth, the force of gravitation between these 2 objects is always going to be attractive. It's always going to pull them together with an equal and opposite force. And that's Newton's 3rd law there, pulling these 2 together with an equal and opposite force, whatever that may be. From what Newton's done, we know that our force due to gravity, F, is equal to this big G, which is a universal gravitational constant. We'll talk about what that number is momentarily, times the mass of the first object times the mass of the second object divided by the radial separation between them. So the distance between them, more or less, from center to center, squared. So GMM over R squared. This value of G here, this universal gravitational constant, it is equal to 6.67 times 10 to the negative 11th, with units of Newton's meters squared per kilogram squared. And this value for the universal gravitational constant G, it only really exists because we have at some point in humans' history defined a meter as being such a length, and defined a kilogram as such a length, and defined a force as a Newton as such an amount. Because of this, we need this value G here just to put these random meters and kilograms into this idea of the Newton. If you were on an alien planet and they had different ideas of what a standard length unit was and a standard mass unit, their value of G would be different. It could be 20 or 1.84 times 10 to the 13th or times 10 to the negative billionth, whatever. Maybe not negative billionth, but you get the idea. It could be a different value. Okay. So if we're looking at something like this, and we have 2 objects, and most of the time whenever we do this, it's easiest to just kind of run calculations, what's known as back of the envelope, meaning that you're not really using your calculator, you're just kind of counting zeros, and we'll talk about that in another video. But if we're just trying to figure out the force between 2 objects, let's just take 2 objects here, like the sun and the earth. The sun has a mass of approximately 2 times 10 to the 30th kilograms, and the mass of the earth is something like 5.96 times 10 to the 24th kilograms. The distance between them is a very special distance. It's known as the astronomical distance, 1.496 times 10 to the times 10 to the 11th meters. We'll just round that up to 1.5 times 10 to the 11th meters. And with just this, we can start plugging values in. We can using our equation F equals gmm over r squared, say that the force acting on both of these planets, equal and opposite, is equal to g, that is our 6.67 times 10 to the negative 11th, times the mass of the sun, 2 times 10 to the 30th kilograms, times the mass of Earth, which is 5.96 times 10 to the 24th kilograms, all divided by that separation between them, 1.5 times 10 to the 11th squared. Okay? Now, if you put this all in your calculator, your calculator should give you the correct answer, and what you're probably going to find is that each and every time you put this into the calculator, it gives you a different one. And you're like, what the heck? The calculator should work the same each time. It turns out that whenever you do these problems for the first time, you're just not used to putting them into your calculator, and you don't really know what kind of number you're getting. The mass of the sun, 2 times 10 to the 30th kilograms, is huge. It's like billions of billions of billions. And 6.67 times 10 to the negative 11th, that's a super small number. So we've got these huge numbers and small numbers, and we're putting them together, and we're getting something on a planetary level. We've never played with numbers like that before, so we don't even know what this answer could be. What we can do here is we could count zeros by just looking at the negative 11, the 30th, and the 24. If we just add those together, 30 plus 24 is 54, minus 11 is 43, and that's over 11 squared. Now, whenever you have something like times 10 to the 11th and you square it, what you're really doing is multiplying it by 2. So this is really like 43 over 22. And if you do that, what you get out of this, each zero up top in the 43 cancels with the 0 down below in the 22. So what you really have is 21 zeros in the numerator left over. So we should have an answer of something like some number times 10 to the 21st or something around that. It turns out when you do this, you get a number for the force as 3.5 times 10 to the 22nd newtons, which is pretty close to the 21st. And we'll see, kind of how to play with that a little bit. So we kind of know that this value, if we get this in our calculator, this is an appropriate value. But I've seen, individuals get numbers like times 10 to the 58th, times 10 to the 34, times 10 to the 8th, like just crazy, like all over the place numbers, but we don't have an idea of what is right or wrong yet when we're talking about space quantities. So just doing these kind of back of the envelope things where we're looking at, how many zeros are in the numerator, how many zeros in the denominator, and just figuring out, hey, this is how many zeros I should have in the problem. That is a really, really helpful thing to do moving forward in this unit, okay? So that's a simple little force problem. Gmm over r squared. You're looking for both masses of the objects. G is a constant, and that r squared is a separation between them, okay? With that, this problem is finished.